Last time we were talking about reactivity of carbonyl compounds. Recall that as electrophiles, carbonyls are reactive at the carbonyl carbon, at the carbon-oxygen pi star. A nucleophile will attack the carbonyl carbon. That's the nucleophilic addition step. Then we get a tetrahedral intermediate, and you can't memorize what happens to the tetrahedral intermediate because it just depends. The tetrahedral intermediate can be protonated to give you this addition product where the nucleophile is on what used to be the carbonyl carbon and a proton is on what used to be the carbonyl oxygen. Or alternatively, if this Y group is a good leaving group, the electrons can kick down and kick off the Y group to give you this product of elimination, then elimination, addition rather than elimination to give you substitution product overall. And we talked about how the identity of the Y group influences the efficiency of this elimination step and the efficiency of the addition step. So the principle on the elimination step was good leaving groups get eliminated. What's a good leaving group? Well, good leaving groups are conjugate bases of strong acids, and we talked about that, and we ranked leaving groups, and we came up with a ranking kind of like this, that a chloride would be a better leaving group than a carboxylate, a better leaving group than a phosphate, better leaving group than a thiolate, better leaving group than an alcohol or an alkoxide. And this was sort of our dividing line because we want a good leaving group relative to what? Notice that in the elimination step, a negatively charged oxygen kicks off the Y group, which ends up with the electrons from the carbon Y group bond. So if the Y group that leaves is more stable, as stable or more stable than a negatively charged oxygen, then probably this elimination step is good to go. So we've said that leaving groups on this side of the alkoxide are probably good to go for elimination reactions. Leaving groups down here, not so much. So H minus, CH3 minus, R, and H minus, not great leaving groups. And we gave some examples of that, predicting that elimination steps would be okay for acid chlorides, anhydrides, phosphates, thioesters, and esters, but not great for aldehydes, ketones, and amides. All right, is that sounding familiar? Any residual questions you have from that? Go ahead.
It would be wrong for the conjugated forms with the conjugate bases, right? So like the carboxylic acid is not the same thing as a carboxyl.
So looking at the leaving groups, to rank them, we considered their conjugate acid pKa's, but those conjugate acids are different leaving groups. The classic example of that, as I said, the amide is not reactive to substitution reactions, but if you protonate it first like this, then it is. And that's because it leaves as the neutral amine whose conjugate acid is 11. That's a better leaving group than an alkoxide. So the principle here is for esters and amides, nature can use proton transfer to make a bad leaving group better. And we'll see some of that in the mechanisms that we consider. Okay, other questions? Yeah. I am recording, yep, thanks. All right, so that was the elimination step. The second thing we were considering is the addition step, nucleophilic attack. And the key question there is how electron poor is the carbonyl carbon? And that's influenced by the ability of the Y group to be a resonance electron donor. Here's the resonance structure where you've got a positive charge on the carbonyl carbon indicating that that carbon is electron poor. And if the adjacent Y group has a lone pair, it can donate that lone pair to form a pi bond between the carbonyl carbon and the Y group. And that pi bond spreads out the positive charge onto the Y group, and it makes the carbonyl carbon less electron poor. And that's important. If the carbonyl carbon's not very electron poor, then a nucleophile isn't going to be attracted to attack it as much. So how can you tell what groups are good electron donating groups? And the key questions that we looked at were, number one, does it have a lone pair? If it does, it can be an electron donating group. And then number two is if it has a lone pair, how good of an electron donating group is it? And we've seen that lone pairs on electron donating groups are more reactive if the Y group is a conjugate base of a weak acid. In other words, if Y minus is a really strong or really reactive base or nucleophile, then it's going to be a better donating group. So we see here that the acid chloride is less reactive than the anhydride because Cl is a poorer donating group than the carboxylate. And why is that? Well, because the carboxylate is a more reactive base than Cl minus. That means here the carboxylate will be a better electron donor. And same thing with the phosphate and the thioester. We compared esters to amides, concluding that the amide, the nitrogen, is a better electron donor than the ester because nitrogen's less electronegative than oxygen. So you'd predict for nucleophilic attack basically the same order that we looked at previously for elimination. The two big exceptions are aldehydes and ketones. And the problem here is aldehydes and ketones have cruddy leaving groups, but they also, their cruddy leaving groups lack lone pairs. So they can't donate into the carbonyl carbon. The carbonyl carbon is still very electron poor. And so these aldehydes and ketones are highly reactive in that nucleophilic addition step. Even though they can't do the subsequent elimination step, they're really great at that nucleophilic addition step. Okay, questions about donating groups? And then the last thing we did was rank molecules in terms, oh, I guess we should mention this. Nature can work even with cruddy leaving groups and excellent electron donors using proton transfers. Just as we saw with the amide before, turning a bad leaving group into a decent leaving group by protonation. So you can turn a molecule that isn't very reactive to nucleophilic attack into one that is by protonating the carbonyl oxygen to get this oxonium ion, which actually has a full positive charge, mostly on the carbonyl carbon, and is much easier for a nucleophile to attack. So basic themes are good leaving groups promote elimination, poor electron donors promote nucleophilic attack on the carbonyl carbon. You can make a bad leaving group better with a proton transfer reaction, and you can make a not very electrophilic carbonyl compound even more electrophilic if you do proton transfer. Lastly, we grouped molecules into sort of three levels. We said you have aldehydes and ketones combined with thioesters, acyl phosphates, acid chlorides, and anhydrides. Though these two, the chloroacid chloride and the anhydride, biology generally doesn't use. These four, though, biology uses all the time. Next was esters. Notice that the oxygen on the ester is a better electron donor and a poorer leaving group than the sulfur in the thioester. So the ester is one row down in terms of reactivity from thioester. We also included phosphoesters because of an analogy between carboxylic acids and phosphoric acids. Below the ester is the amide. The amide is a better electron donor. The nitrogen's a better electron donor and a poorer leaving group than the ester, so it's less reactive. And then level 4 is the carboxylate, which is not even an electrophile. The carbonyl carbon in the carboxylate is not electron poor because you have this adjacent negative charged oxygen that donates electron density into it. And so the carboxylate is the low end of our ladder of compound electrophilicity. Carboxylates aren't good electrophiles. Okay, questions about that ranking? That'll be important for what we want to talk about today. The last thing was introduction of new functional groups. We used phosphates as carbonyl analogs. So here's a carboxylic acid group, here's a phosphoric acid group, carbonyl group, phosphoryl group, comparable pKa's. The difference is that phosphoric acid has additional protons that can be removed with pKa's of 2, 7, and 12. We said that a carboxylic ester looks like this. A phosphoester is where one of the OHs of phosphoric acid has been replaced with an OR group. They're similar in stability and reactivity because of the identity of the leaving group and its electron donating properties. So we put the phosphoester here. We also put phosphate here because it's similar to the carboxylate. The last thing we did is we talked about this acyl phosphate that we've already seen as a reactive carbonyl derivative. And I pointed out how normally we've thought about nucleophile attacking the carbonyl carbon to get a tetrahedral intermediate. But the nucleophile could also attack the phosphoryl group at the phosphorus, and electrons kick up onto the oxygen. That would give you this intermediate, and then electrons on the negatively charged oxygen could kick down and phosphate could leave, and that would convert a high energy level 1 compound. Depending on the identity of the nucleophile, one of the products here is a level 4 compound, so we would expect that to be downhill. All right, that's our review. Anything you want to ask about that? Okay. Well, in addition to acyl phosphates, there are other kinds of phosphoryl compounds that you want to be familiar with in this class. One of them is ATP, and ATP is going to be an example of a level 1 molecule. So in ATP, you've got a 5-membered ring containing oxygen. And then I'm going to abbreviate the structure of ATP with the letter A there. That stands for the adenine base, which we'll see later today. I'm just not going to draw it. That's the A in ATP. There's, let's see, a wedge here, an oxygen, and then ATP is really interesting because it has 3 phosphoryl groups linked together via oxygens. People call this the alpha phosphoryl group, the beta phosphoryl group, and the gamma phosphoryl group. And the confusing thing about ATP is, depending on your perspective, you could think about any of the phosphoruses as being electrophiles and everything else being a leaving group. Let me give you an example of that. Suppose this phosphoryl group were reactive. You might expect a nucleophile, and I'm going to be generic about that nucleophile. Let's let it be an alcohol. Could attack this phosphate group to give an intermediate with a negative charge on the pink oxygen. In that case, all of this is the leaving group. Now that may look strange, but let's look at it after it leaves and see if it makes sense based on stuff that we know. All right, so let's draw the intermediate where we just made a new bond between phosphorus, between phosphorus and the oxygen of our purple nucleophile. There's the OR group and the new bond we made with the phosphorus. I'm really tempted to copy and paste, but since I know some of you are writing with pen and paper, we'll just draw it out and deal with it. All right, so this is the intermediate. It's not a tetrahedral intermediate because the phosphorus is surrounded by 5 things, but it's like the tetrahedral intermediate we've seen before in carbonyl chemistry. This is the oxygen that's going to be the kicker-offer group. Lone pairs on that oxygen do an elimination step. So this first step that we did would be the addition step. And then the second step is the elimination step. And the leaving group leaves. So let's draw what we make after that. Here's the RO group. And that functional group at this point is what kind of phosphate molecule? It's not phosphoric acid because it's got an OR group. What do we call this carbonyl with an OR group on it? That's an ester. So a phosphoryl with an OR group on it should be a phosphoester. Good. So that's level 2? Yeah. That's level 2 on our list of reactive compounds. So we went from ATP, which was level 1, to phosphoester, which was level 2. And then let's look at the leaving group that left, the thing that we highlighted in green. The thing that left is ADP now. The D stands for diphosphate, meaning there are 2 phosphoryl groups in this molecule. This is the green leaving group. And the question we can ask ourselves is, was it a good leaving group? To do that, we compare it with its conjugate acid, which I'm going to do by copy and paste. Here's the conjugate acid of the leaving group. You put a hydrogen on the atom that used to be attached to the phosphoryl group. What is the pKa of that hydrogen? If we look it up, if it were an alcohol, it would be 16, but the number we're looking for is for some kind of phosphate group. We want to know the pKa of a monoanion, which is around 7. Because I'm just, you could say, well, there's another negative charge there, and you'd be right, but I'm just focusing on this group. And I'm guessing that the pKa of this hydrogen is around 7.2, which would mean, based on our description, that this is a good enough leaving group to be kicked off by a negatively charged oxygen. So this is why ATP is a level 1 molecule, because if the nucleophile attacks at the gamma phosphoryl group, then everything else is a decent leaving group. Yeah?
So when we're looking for a leaving group, I know for one problem that we did, it was the left group. I don't know, are we always looking at the right group when we're looking for a leaving group? Or can we occasionally look at the left?
Are you talking about ATP in specific, or are you just saying in general? I mean, I can draw the carbonyl compound any way I want. So I could draw it this way, or I could draw it this way. So it may not always be on the left or the right. That's not the answer to your question, though.
So I guess, how are we supposed to determine what the leaving group is?
So
Like
you...
in its whole statement.
2 ways that you can determine what the leaving group is. First, with practice, as I show you, what I'm going to do as I start teaching you mechanisms is I'm going to show you starting materials, I'm going to show you intermediates, and I'm going to show you products, but I'm not going to give you any arrows. And based on, if you look carefully at starting materials, products, intermediates and products, you will be able to tell what the leaving group is because it leaves. Once you get that experience, you'll get used to looking at something like ATP and saying, if somebody attacked that phosphorus, everything over here could be a good leaving group. The functional group that we're talking about, the bond between a phosphoryl group and then a phosphate-based leaving group is similar in some ways to the bond between a carboxyl group or a carbonyl group and a carboxylate leaving group. And you could ask the same question, I think, that you're asking about ATP as you asked about this anhydride. In other words, there's some symmetry to this molecule called an anhydride. It's a carbonyl on one side and a carboxylate on the other side, and a nucleophile could attack here. But you might be asking, well, what if I shift my perspective and this is now the leaving group and then I want to attack at the other side? That's fine too. In fact, in this case, they're both symmetrical. But we're going to call this kind of bond between a phosphoryl group and a phosphate leaving group a phosphoanhydride. And I don't have enough space to write that. Phospho-anhydride. And so we'll get better at recognizing phosphoanhydrides, and when you see them, you need to think one of those phosphoruses could be attacked, and the other could be the leaving group. Yeah, go ahead.
I was just gonna ask, could the nucleophile attack one of the phosphorus beta or alpha?
Yeah, can the nucleophile attack either the beta or the alpha? It can. The two places that ATP gets attacked in most biochemistry is at gamma and at alpha. Generally not, for some reason, at beta.
So if it were to attack at alpha, would it just make the leaving group just the AT?
Yeah, if we attack at alpha, what would the leaving group be? I'm sorry, so what I meant to label, what I've shown you here is attack of ATP at the gamma phosphoryl group. Okay, let's do attack of ATP, and the product there, by the way, was a phosphoester, or whatever this OR group was. Okay, let's just show you generically attack at the alpha phosphoryl group. So we'll just draw ATP again. You're going to get a lot of practice drawing ATP. You're going to be sick of drawing ATP if you aren't already. And thankfully, I decided not to draw the adenine base part of ATP. Here's the alpha phosphorus, the beta phosphorus, and the gamma phosphorus. If we attack the phosphoryl group alpha, then you have to choose, because that phosphorus is attached to two things. You got to choose which side is going to be the leaving group. You've got two options. You could do this side, or you could do this side. Now let's just think that through for a little bit. If we did this one as the leaving group, the leaving group would look like this. Alternatively, if we did this one as the leaving group would look like this. Which of those do you think is a better leaving group? This one is an alkoxide, and this one, just focusing on this part of the molecule, is a phosphate dianion. To rank their leaving group abilities, if you're getting the intuition, you're getting it, you already know which one it is, that's fine. If not, the conjugate acid of an alkoxide is an alcohol with pKa of what? 16. Conjugate acid of a phosphate dianion is a phosphate monoanion, which has a pKa of 7.2. The better leaving group is the conjugate base of the stronger acid. So yeah, the better leaving group is going to be the one that leaves. And this is a general principle in elimination steps. The better leaving group leaves. So I think that answers your question about which one gets kicked off. So if a nucleophile were to attack, let's just have it be another alcohol. We're considering prospective leaving groups. This one is the best leaving group. So we would have the alcohol, lone pair electrons on the oxygen, attack the phosphorus. We would get the intermediate where the phosphorus is bonded to 5 things. Whoops. The pink oxygen's going to be negatively charged. We're going to have a new bond in red between the phosphorus and our OR minus nucleophile. Over here is another negatively charged oxygen. Over here is the oxygen from the 5-membered ring. Here is the adenine base. And then here is that beta and gamma phosphate groups as leaving groups, which I'm sorry started. Oh, and somebody should object to that. I missed an oxygen, right? There we go. Was kind of hurrying and my hand was getting tired, so I glossed over it. Okay. That's not very aesthetically pleasing, but there you go. This is our leaving group. Electrons on the negatively charged pink oxygen kick down, leaving group leaves. And our 2 products are, oops. This one, now our OR group is attached to the blue alpha phosphorus, which is itself still attached to the ring of the sugar, and an adenine group. And then over here was the leaving group, which we already looked at and decided would be a better leaving group than the alternative. And here, our nucleophile is now attached to something called adenosine monophosphate. Okay, so there are 2 different ways you can see ATP reacting. One of them is attack on the gamma phosphate group, and then ADP is the leaving group. And then the other is attack at the alpha phosphate, and then the beta and gamma phosphates are the leaving group. And this molecule with the beta and the gamma phosphates together has a name. It's called pyrophosphate, and it's important in a lot of biological reactions. All right, questions? Go ahead.
So just for like a simplicity form, whenever the nucleophile goes to attach to the electrophile, it's always going to keep the pi bond up to the oxygen.
Yep.
And then to be able to make it a leaving group, those lone pairs will always come back down to kick off.
That's right. Yep, lone pairs always kick down to kick off the leaving group. And I'm missing an arrow there, aren't I? Electrons kick down, so this is the elimination step. And similarly, notice the pattern. Addition here to the carbonyl carbon, electrons kick up. Intermediate with a negatively charged carbon, negatively charged oxygen, then electrons kick down and leaving group leaves. Yeah, that's the pattern. Go ahead.
How would we know the conjugate base? Like, would we have to know the conjugate base of like a molecule, like the
The molecule on the end of ATP.
Like when comparing the pKa's between like which leaving group you would want.
Oh,
Like,
we were making,
but
yeah, we were trying to make that assessment here as we were thinking which side is going to leave. You have to do your best just to figure out what the right leaving group is and what the right pKa to use for its conjugate acid. I recognize this, even though this whole molecule isn't on my pKa table, I recognize it as the conjugate base of an alcohol. So I just choose the closest thing I can find. Similarly, as I look at the prospective leaving group of this pyrophosphate group, I'd be like, well, that's not on my pKa table, but I do have a phosphate dianion, and the phosphate monoanion that I could find on that table does have a pKa of 7.2. Yeah, so you're just looking for something that's close enough. With experience, you probably won't even need to use the pKa table anymore once you get used to starting to see the pyrophosphates, the better leaving group. All right, yes?
I just have a question. So I understand why we're looking like at leaving groups and stuff, but when are electron donating groups important, and where does that play into all this?
So electron donating groups are important as we've used them to recognize. We basically use the concept of leaving groups and electron donating groups to come up with this, this ranking of biological molecules in terms of reactivity. The most reactive carbonyl compounds, the level ones, either have excellent leaving groups, which is the case for these four here, or if they don't have excellent leaving groups, they have really, really poor electron donating groups. Okay? Those are two ways you can be reactive. The really good leaving groups promote both, promote the elimination step, and the molecules and the poor electron donors promote the addition step. And then we say that esters, because this is a poorer leaving group than the ones up here, we put it in a different category. It's also a better electron donor than the ones up here. So it's a worse leaving group, and as a better electron donor, the carbonyl carbon is less electron poor. And then we make that same conclusion for the amide. Yeah. Yeah.
Explain the thing that you said just a couple minutes ago about when it attacks on the alpha, which ones are the leaders and
Sure. When you attack on the gamma phosphate group, the only choice you have for the leaving group is ADP, this segment over here. If you attack on the alpha phosphorus, you got two options. Once you get to that tetrahedral intermediate, the thing that could have been kicked off was either the green pyrophosphate group or the orange alkoxide group. And so to make that to make the decision who gets kicked off, the better leaving group always gets kicked off. So what I did is I drew the green pyrophosphate as it would appear after it had been kicked off, and I drew the orange alkoxide as it would appear if it got kicked off. Then I compared the pKa's of their conjugate acids. This, the orange thing is an alkoxide. Its conjugate acid is an alcohol who has a pKa of 16. In contrast, the green leaving group is a phosphate dianion. Its conjugate acid is a phosphate monoanion with pKa of 7. Stronger acid, better leaving group. All right, so if we were gonna add to our list of level 1 reactive molecules, I'm going to copy this from the notes from last time and put it into today's notes. If we were going to copy this list, I would include as level 1 compound, as level 1, in addition to acyl phosphates, I would include ATP and anything with a phosphoanhydride linkage. And we'll see lots of examples of that a little bit later. All right. So keep that in mind. We're now going to talk about why and how reactions happen. The issue of how a reaction happens is exactly what we have been doing with ATP today. When we use arrows, we're showing a mechanism, okay? In contrast, when we talk about why a reaction happens, what we're really asking is, what is the relationship between starting materials and products? Are the products more or less stable than the starting materials, or are they about the same stability? That will help us know whether the reaction is very downhill in energy or uphill in energy or perhaps neutral. So the question of why a reaction happens to answer that question, we must compare the stability of starting materials. For some reason, I like saying starting materials better than reactants. I don't know why. Starting materials is longer, but compare the stability of starting materials and products. So, for example, imagine a reaction where we have a starting material going to a product, and you imagine, is the reaction favorable? If the reaction is favorable or downhill, the only way that can happen is products are more stable, or alternatively less reactive than starting materials. Unfavorable would be uphill, and that would be that products are less stable, that is more reactive than starting material. And neutral, which would be meh, is products and starting materials are similarly stable or reactive, or alternatively reactive. Okay, and this is why we took the trouble to go through and identify level 1, level 2, level 3, level 4 reactivity. So with all this in place, we're now prepared to look at reactions that you've never seen before, and by analyzing whether the molecules are level 1, level 2, level 3, and so on, determine whether it's uphill or downhill in energy. So let's do the first, if you go to your quiz, question 1, predict whether the following reactions are uphill or endothermic, or downhill, exothermic, or neutral. And let's do just the first one on the list. Let's see, where are we? Here we go. Let's do that first one together. So this reaction is called saponification. This is actually a soap-making reaction that our ancestors used to do. You take animal fat or lard and lye from ashes, and you break the ester in the triglycerides. This is just a monoglyceride, and you get glycerol and you get fatty acids. So, looking at the starting materials on our left, what is the key functional group in the starting materials that disappears in the product? Okay, I heard somebody say alcohol. An alcohol does appear, for sure. What about the starting material disappears? Starts out as a monoglyceride, a large nonpolar tail, a carbonyl carbon, and then an OR group. And then over here, it's a long tail and a carboxylate, and my OR group has left and become an alcohol. So what's the carbonyl in the starting material that's changing? What kind of functional group is that? Ester, right. Remember, how do you recognize an ester? Well, an ester will have a carbonyl carbon, a carbonyl oxygen, and then for an ester, the leaving group is an OR group. Okay? What level of reactivity is the ester? 2. Okay, good. Not as highly reactive as an aldehyde or a ketone or a thioester, but more reactive than an amide. Then, if we look at the product here, the product is an alcohol, but we're going to focus. It's true that a full, complete analysis here would require us to also compare the stability of the negatively charged thing here and the stability of the alcohol. But we'll get the right answer for the most part if we focus on the carbonyl compounds. And since this isn't a math class, we're not looking up numbers, we'll just focus on the carbonyls. What kind of carbonyl compound is the fatty acid? Carboxylate. It's got a long nonpolar tail, but you can recognize the carboxylate because it's got a carbonyl carbon, a carbonyl oxygen, and then in place of the leaving group, it's got a negatively charged oxygen. What reactivity is the carboxylate? 4, right? So level 2 to level 4, do you anticipate that being downhill, uphill, or neutral? Downhill. Because you go for something that is less, you go from something that is less stable, more reactive, to something that is more stable or alternatively less reactive. All right, so that's very downhill in energy. Good. Now, look at the horror that is the next one. That's fun, isn't it? Here on top are starting materials. On the bottom are the products. This is a molecule called coenzyme A. Basically, this is the actual structure of coenzyme A. And the reason I'm drawing it for you is because this section in here, from this oxygen to this carbon, is actually an essential vitamin. You got to have it in your diet. It's vitamin B5. It's called pantothenic acid. And that becomes part of this large molecule coenzyme A. The A stands for adenine. There's the adenine base. All of that you can think of as an R group, and this sulfur in this reaction is going to be your nucleophile. Okay? Then this molecule here is called a fatty acyl AMP. It's got a long hydrocarbon tail, a carbonyl oxygen, carbonyl carbon, carbonyl oxygen, and then a phosphate group over here. This is an example of an acyl phosphate functional group. Let's just talk through it and see if you can figure out what is happening in this reaction. Take a look at the products. I've already told you what the nucleophile is. That means that the acyl phosphate is likely the electrophile, meaning it's going to get attacked. See if you can find a carbonyl group attached to a leaving group, or alternatively, a phosphoryl group attached to a leaving group. Look at the products and see which atom in the electrophile got attacked. Let me give you a hint. The key portion is here. the carbonyl oxygen, the carbonyl carbon, and then we've also said that you got to worry about phosphoryl groups too. They can be attacked as well. So look at the products and see which bond the sulfur gets attached to, which atom the sulfur gets attached to. If you're struggling a little bit, pay attention to the products and see if you can figure out what the leaving group was. Well, that, it looks like an ester that the leading group is the phosphate, so that's an acyl phosphate.
It's not.
A phosphoester is where the phosphorus is attached to molecular particles in alcohol.
But this isn't.
No, that's a carboxyl. So that's all I wanted to do is to compare ultimately the product is to identify the functional characteristics and compare is it the same level or different levels. Okay, any questions as you're considering this? Keep in mind, we're not yet talking about how. You don't have to know the arrows yet. We're going to talk about the arrows. We're just dealing with what and why. So, and I wanted you to look and figure out what happened in this reaction. The nucleophile was the sulfur. And the best way to figure out, what did you come up with? What do you think the leaving group is? Of the two products, which one would you call the leaving group? The AMP. Okay, good. This is the thing that used to be attached to a carbonyl carbon, but now no longer is, right? So that would seem to indicate that all of this is the leaving group. Now that I've highlighted stuff in green, it becomes clearer, but how did you see that? Or if you're struggling to see it, tell me more about that. Yeah, go ahead.
Well, I just remembered on the ATP example that we did, but maybe that's cheating, but
No,
I just thought.
You're allowed to use knowledge that you have previously, so that's okay.
But I just recognized that we attacked that phosphate group with a double bond, and then I was looking at the bottom molecule, and at first I looked at what was the group that was broken off, and then I tried to find out which molecule where that originated from.
Okay.
And that's kind of.
Good, yeah, so a couple of ways to work your way through this would be either starting with the leaving group, looking what gets broken off the electrophile. The AMP thing there, the two rings with the nitrogens in them, that's called the adenine base. This is the ribose ring, and this is a phosphate group. Those were all present in the electrophile, but now they're not, which tells you that in this reaction we broke this bond. between oxygen and carbon. The other thing you can do is look at the nucleophile, and I told you the sulfur was the nucleophilic atom. The rest of this was just an R group. Why does nature bother with the rest of this? Well, the enzyme has to have something to hold on to. This is the handle that the enzyme uses to move the nucleophile to the right place. Then look where that sulfur is in the product. And it looks like it's attached. So I'll just start, we'll use gray for the everything else on the nucleophile so we don't get confused. This is the everything else on the nucleophile. That must mean that this bond here is the one that we made. And look at what it's bonded to. It's bonded to a carbonyl carbon and the carbonyl oxygen. Oh, and there's my nonpolar tail for this fatty acid. Okay? Questions about that? Yeah.
When we're comparing the levels, do we compare the level of the leaving group that I made or the bond?
That's an excellent question. When you're comparing levels, should you compare the leaving group or the bond that's made? Technically, you should do two things. You should compare the levels of the carbonyl compounds, starting material and product, and then you should also compare nucleophile and leaving group. Now, for our purposes, we're not going to do the nucleophile versus leaving group. We would do that if you were taking OChem. What we're going to do, it will get to just close enough to the right answer by dealing with just the carbonyl compound. So, identify in the electrophile where's the carbonyl or phosphoryl carbon that gets attacked. You do that by identifying what the nucleophile is bonded to in the product. Then you ask what kind of carbonyl or phosphoryl compound this is. This is an acyl phosphate. Then you consult the list and remember that's level 1. It's level 1 because the stuff in green is a good leaving group. Now let's look at the product. The product has the carbonyl carbon, carbonyl oxygen, and now it's attached to what used to be the nucleophile. What kind of functional group is this? See if you can find it on something that's similar on this list. You may not know what it's called. It's the carbonyl group attached to a sulfur or thioester. Okay? You can recognize it as a thioester because carbonyl, carbon and oxygen, and then a sulfur instead of an oxygen, an SR group. So that's thioester. That's also what level? Level 1. So then conclude, is this reaction uphill, downhill, or neutral? Neutral. Good. Now this reaction is one of the steps in how your body makes triglycerides. Yeah, go ahead.
I'm a little confused, I guess, how the glycerol and the AMP, how it gets the extra alcohol.
Okay, yes. So one of the things you're noticing is there's a proton on glycerol, and you're thinking the leaving group should have had an O- on it, right? Similarly, you're noticing that here the leaving group has a proton on it, whereas here it should have been O-. The proton that's here, let me show you where it technically comes from. And again, this is, I did the reactions this way so there wouldn't be issues of, well, the charge changes. But if you follow, there used to be a proton on this hydroxide that attacked. That's the same proton that ends up there. How it gets there, we'll have to draw the mechanism for it. Similarly, there used to be a hydrogen on the sulfur nucleophile. In the thioester, there isn't. Where did it go? It ends up right there, just to keep everything balanced. Yeah. Okay, now tell me a little bit more about your process and what's hard about this. Because I've been doing this for long enough that I'm used to looking at big molecules, zooming in on the key functional group, and figuring out what to worry about. But I understand that when you're first new at this, you look at that and you think, what am I supposed to do with all of that? So, what is your process for looking at something like that? What would work for you to look at something like that and focus in on the parts that are important? Identify carbonyl carbon or phosphoryl carbon. Go ahead.
I just look for double bonds with oxygen first.
Okay, so you're starting with double bonds to oxygen because that'll attract your attention to carbonyls.
Cool.
Go ahead.
I also look for groups that like there's only one of it in the molecule and see where it ends up. So like the sulfur was helpful because there's only one of it. We just compare it to where it is.
Okay, that's another clue as you look at a reaction. If there's only one of something, it becomes easier to follow it through. There's only one sulfur in this reaction, and so you can follow where it goes. Good. Other things that you've learned in this process that might be helpful tools. Go ahead.
It's very helpful to like circle or like black out on things that stay the same because they don't really involve anything, so you just like
That's right. So pay attention to starting material and product. Focus on what changes, not what stays the same. So, you know, if you're doing this on an exam, you don't have you could bring highlighters if you want. More power to you. Bring highlighters. You can write on the exam, or you can shade things, but that can be, or put them in a box or circle them or have a special symbol that means I think I can ignore this for now. Yeah, good. What else? Yeah.
For like identifying which one's the leaving group, I just would look at like what product is like something that's entirely the same and like not something new.
Right. So if in the leaving group, identifying the leaving group, it's going to be exactly the same as it was in the starting material, only it's going to lack a bond and it's going to be just itself. Good. Okay. Any other helpful tips? Okay, well, we need a break and then we're going to continue on with the next 2 or 3. So, yeah, let's take about 5 minutes and then we'll keep on going.